me just go straight into it, right? So we have B8, right? So this was a problem looking at the expansion of CO2 under a few different conditions, right? One is isothermally and reversibly, one is isothermally and irreversibly, and then one is adiabatic and reversibly. So that way, there's different equations that you use. There's going to be, right, because of the different conditions, there's going to be different, um, you know, things that are going to end up equaling zero or being equal to each other in those cases. And so my goal right now, right, is going to be to try and kind of highlight what those things are, so that way you guys can, know how to approach these problems, right? So in this case right here, let me just go ahead and just start writing out what the conditions are that we have. So we have, 2.5 moles of CO2. We're, initially at a temperature of 293 K, right? We have an initial pressure of 2.50 atmospheres, right? We expand it until we're at a final pressure of 100 atmospheres, right? And so then from there, right, it says it gives us the CP value in this case, right? So CP, let me go back one, right? So CP is equal to 37.1 joules per Kelvin mole. And we can assume that the gas behaves ideally in those cases, right? So what it wants us to do is calculate Q, calculate W. All right, let me just delete this, right? Q, right, heat, work, delta E, right, the change in internal energy, the change in entropy of the system, change in entropy of the surroundings, and change in entropy of the universe. So looking at the first conditions that we're at, right, we're isothermally and reversible. So if we're isothermal, there's a few things that we already know right off the bat, right? So the first thing that we know about an isothermal expansion of an ideal gas is that delta E is going to be equal to zero, right? So right off the rip, we already know that part. So that's already done. We already figured out delta E just by reading the problem. The next thing that we know is that Q is going to be equal to negative work, right? So all we have to do is just calculate one of those two, and we can just easily then get the other one, because all we have to do is just multiply that by -1, and we get that, right? So there's really only one equation that we have to use to knock out those two right there. The next thing, right, that we know off the bat is then that because it's a reversible expansion, that means that delta S of the universe is going to be equal to zero, right? So again, that's completely taken care of. That's out of the system, so we don't have to worry about that part right there, right? So that's done. Because delta S of the universe is equal to zero, right? We know that delta S of the universe is equal to delta S of the system plus delta S of the surroundings. And so based off of that, right, we again know that delta S of the system is going to be equal to negative delta S of the surroundings. So again, all we have to do is just calculate one of those, and then we figure out what the other one is by just multiplying by -1, right? So in essence, for this specific problem, there's only two equations that we're going to have to apply, right? We're only going to really have to calculate two things using this information to get, our values and informations and whatever stuff here. So to do that right there, right? So now the next question is what equations to use, right? So for isothermal and we're reversible, the equation, right, that we would want to use in this case right here to do the Q and the W stuff is we know what the equation is for reversible isothermal work, right? So that equation is, right, work reversible is equal to negative nRT natural log of V2 over V1 in this scenario, right? So we know what is going on here in those cases, right? So what we just need to then now do, because we know what N is, we know what the temperature is, right? That's 293 Kelvin. R is just simply the gas constant, right? The 8.314 joules per Kelvin mole. The only thing we need to now figure out is what the initial volume is and what the final volume is, right? We don't have those calculated. They're not given to us in the problem. So all we have to use is the ideal gas, law in this scenario. So to calculate, right, what V initial is, right, we know the ideal gas equation is PV equals nRT. So if we just rearrange this right here, right, we have V is equal to nRT over P. Right. And so in this case right here, right, so for V initial, we can just apply that right there. So if we have that, right, V initial is going to be equal to N. So that's 2.5 moles times R. So now the thing with the R, right, because in this case right here, we're trying to get liters as our answer, right? And we're given, a pressure in atmospheres, we're going to use a different gas constant, right? Because that's going to have different units in this case. And so the gas constant that we're going to use here is 0.08206 liters atmospheres over Kelvin mole, right? And then that is, let me just delete this stuff out of the way, right? Times the temperature in Kelvin, right? So that's 293 Kelvin. And then that will be divided by the pressure, right? So the pressure initial is 2.50 atmospheres, right? And so if we're looking at it, right, we can see atmospheres cancels. We can see that the moles cancel. We can see the kelvins cancel, right? So we only end up with liters as our unit in this scenario. So, right, we plug all of this now into our calculator. So we have 2.5 times 0.08206 times 293 divided by 2.5. What we get is an initial volume of 24.04 liters, right? So that's our initial volume in this case right here. And so then the next thing is, what does the gas expand to? So if we have V final in this case right here now, right, we can do two approaches, right? We can just simply do, P1 V1 is equal to P2 V2, right? Or we could also just simply plug everything into the previous, equation that we had for V, V initial, and just simply switch out the 2.5 with a value of 1 in that case, right? So I'm just going to simply, though, do the P1 V1 is equal to P2 V2 because that makes it a lot easier here, right? So we have then essentially, right, P initial times V initial is over P final in this case, right? So if we take that right there, P initial is 2.50 atmospheres times initial volume, right? So that's 24.04 liters. Divide that by final pressure, so that is 1.00 atmospheres. Atmospheres cancels, we get liters. So what we have now in this case is 2.5 times 24.04 divided by 1 comes out to 60.1 liters, right? So that's what we're getting in this case for what's going on for this expansion. So now we have, right, V final, V initial, so we can just plug that into up here. So now we just plug in our value. So we have negative, and then the N value, right, is 2.5 moles. Our R now, right, because we're looking for a final value of, a final unit of joules, right? We're going to use then the 8.314 joules per mole Kelvin, right? Times the temperature, right? So that in this case is 293 Kelvin, times the natural log of V2, right? So that's going to be our V final. So that's 60.1 liters over our V initial, which is 24.04 liters, right? So moles cancel, kelvins cancel, right? Liters cancel. So we're only going to be left with joules, right? And that works for what we want, right? So we have work reversible is going to be equal to that. So if we just plug this in, so negative 2.5 times 8.314 times 293 times the natural log of 60.1 divided by 24.04. Right? And so what we get is negative 5,580 joules as our answer, right? Which matches what I have on the key, right? Which is negative 5.58 kilojoules. Right, so we have that right there. We have the work reversible. Now, right, we know that Q is equal to negative work. And so if we just plug in, right, what we have here, so negative of negative 5,580 joules, right? That gives us 5,580 joules, positive as our answer. Sorry, there's a lot going on with the other class that I have. Yeah, right. So that's how you get Q, right? So that part is done, right? We're done with Q. We're done with work. We're done with delta E. Now we just need to focus on the entropy part. So now for the entropy, right? All we have to use is the equation, delta S of the system is equal to Q over T, right? We can just simply, use that value right there for what we're looking at. Excuse me. Right. You could also use a different equation, right? You could also just simply be like NR natural log of V2 over V1. But if you were to derive the equations, right? So the NR natural log V2 V1 is technically the correct way to calculate the delta S system, but we can just skip all of that because we know, right, that Q, right, is equal to nRT natural log V2 over V1, right? And the reason that we know that is because, right, it's going to be equal to the negative of the reversible work, right? And so that starts off with a negative right there. So if we just simply cancel those out, we don't have to worry about that, right? So this is just simply a shortcut. So that way we don't have to plug a whole bunch of things in, right? We just have to plug in our Q value and divide that by the temperature in this case, right? So the delta S of the system is going to be equal to Q over T. So that's going to be equal to 5,580 joules divided by the temperature, which is 293 Kelvin. And so what that comes out to being is 5,580 divided by 293. That comes out to being 19.04 joules per Kelvin, right? Which is what I have on the key in this case right here, right? So that's the delta S of the system, delta S of the surroundings, right? We know that that's going to be equal to negative the delta S of the system in this specific scenario, right? So all we have to do now is just simply take, negative 19.04 joules per Kelvin, and that's done, right? So we've calculated everything. All it really took was figuring out what the two volumes were, figuring out what the work reversible was, and then just simply multiplying that by -1 to get the Q. And then in the case of the delta S system, just taking that Q, then dividing that by T, and then multiplying that by -1 to get the delta S of the surroundings, right? And then we know that delta S of the universe, right, is going to be 0 because it's a reversible process, right? So very straightforward. Again, my biggest recommendation is going to really be, in preparation for the exam, which is in about week and a half, take a moment, right, and then just take stock of all the things that are going to, all the conditions, right, that you automatically know just by reading the problem, right, in terms of what's going to be equal to what are the equations that you have to use for everything, right? And then, what's going to be equal to 0, right? Because there's a fair amount of scenarios where you're going to have, things that are going to be equal to 0, right? So in this case, it's delta E is equal to 0, delta S universe is equal to 0, right? So that's pretty straightforward there. So